In this video, we're going to discuss graphical antidifferentiation. Just thinking back to the derivative for a moment, we know from Calc 1 that if we're given a formula for a function, we can compute the formula for its derivative. We also spent some time looking at graphs. If we're given the graph of a function f, how can we graph its derivative function, even without knowing the formula? Well, we're going to consider the opposite questions now. First, given a formula for a function, can we compute a formula for its general antiderivative, capital F, which of course we denote using the indefinite integral notation. This type of thing we've done plenty of already. For example, if we want to find the antiderivative of cosine of x plus x, we can express that using indefinite integral notation, or I'll denote it as the function capital F of x. An antiderivative of cosine is the sine, and an antiderivative of x is x squared over 2. And then we have to add the plus c. We have to add the plus c because the antiderivative is not a single function, it's actually a family of functions. But let's say we wanted an antiderivative that passed through a specified point. Let's just say, for the sake of argument, that I want my antiderivative graph to pass through the point 0, 1. So that means capital F of 0 is 1. So let's substitute 0 in for x here and set the result equal to 1. 1 equals f of 0. And if I substitute 0 in here, I'd have the sine of 0, which is 0, plus 0 plus c. So c would have to be 1. So the antiderivative that passes through this specified point would be given simply by this single function. Now let's take a look at things graphically. Given the graph of a function, can we graph its derivative, its antiderivative, provided we are told that the antiderivative graph passes through a particular point? So we have some tools at our disposal. The fundamental theorem of calculus. It says that if little f is continuous on the interval from a to b, and if capital F is an antiderivative, then the integral of little f from a to b is what we get when we substitute the endpoints into the antiderivative and subtract. We also have graphical relations. We know that if a function capital F is increasing on an interval, that's the same thing as saying its derivative, which is little f, has to be positive there. Or in other words, the graph of little f would be above the horizontal axis. A function capital F is concave up there on an interval, provided its derivative is increasing there. Now typically we think of concavity as being associated with the second derivative, and that is true. If capital F is concave up, its second derivative is positive, but in terms of the first derivative, that means the first derivative is increasing. So let's take a look at some examples just to refresh ourselves. So again, throughout the discussion here, the derivative of capital F is going to be little f. Let's say capital F had a shape like this. Then its slope, which is little f, has to be positive. Capital F is concave up. We can see that as we move from left to right, the slope of capital F, which is capital F prime, is increasing. So therefore, little f would have to be increasing. Let's look at this. Capital F is increasing, so its derivative, which is little f, has to be positive, or has a graph above the x-axis. Capital F is concave down. As I move from left to right, my slopes are positive, but are becoming less positive. So capital F prime is becoming less positive, so it is decreasing, but capital F prime is little f, so little f has to be decreasing. Here's another example. Capital F is decreasing, so its derivative, which is little f, has to be negative. Capital F is concave down. The slope is negative and becoming more negative as we move from left to right. So its derivative, the derivative of capital F, which is capital F prime, is decreasing, but capital F prime is simply little f, so little f would have to be decreasing. And finally, suppose we had something like this. Capital F is decreasing. That means its derivative, which is little f, is negative. We can also see that capital F is concave up. The slope of capital F, which is capital F prime, is negative, but it is becoming less negative as we move from left to right. So capital F prime is increasing, which means that little f is increasing. So we're going to use those ideas together with the fundamental theorem now. We're going to assume we have the graph of this function. So this is the function little f, and we want to graph its antiderivative with the property that it passes through 0, 1. I just chose 0, 1. Now again, we're not graphing the derivative of the function, we're graphing the antiderivative. We want the function whose derivative graph would look like this. So here are some tips to get started. The first thing I would do is look at where little f is positive or negative. It appears to me on the graph that little f is positive. The graph of this, which is little f, is positive or above the horizontal axis if x is less than or equal to, let's say, minus 3.5, or if x is between 0 and 3.5, say. So that's where little f is positive. That means capital F, which is the antiderivative, has to be increasing on the same intervals. Because if capital F is increasing, its derivative, which is little f, has to be positive. Where is this graph above negative? Well, it's negative between minus 3.5 and 0, and if x is greater than or equal to 3.5. So if little f is negative, capital F has to be decreasing. Because if capital F is decreasing, its derivative, which is little f, has to be negative. So first, look at where little f is positive or negative. Then look at where little f is increasing and decreasing. Now little f is increasing from minus 2 to 2. So that means capital F is concave up there, because we said a moment ago that where the derivative of a function is increasing, the function is concave up. So little f is increasing from minus 2 to 2, which means that capital F prime is increasing, which means that capital F is concave up. And then finally, we ask ourselves, where is little f decreasing? Well, little f is decreasing if x is less than or equal to negative 2 over here, or if x is greater than or equal to 2 over there. So if little f is decreasing, that means that capital F prime is decreasing, which means that capital F is concave down. So again, look at where little f is positive and negative. Look at where little f is increasing and decreasing. And once we have the answers to those questions, we can draw our axes split up into zones, so to speak. So what I've done is I've put dots on my horizontal axis at the points of interest, minus 3.5, minus 2, 0, 2, 3, 3.5. So again, the points of interest, the points where the graph of big F might switch from increasing to decreasing, or switch concavity, would be at minus 3.5, minus 2, 0, 2, and 3.5. Now, to the left of minus 3.5, we know that capital F is going to be increasing. In here, we know that capital F will be decreasing. In here, we know that capital F will be increasing, and then it will be decreasing over here. And again, we know that from what we established right here. So I drew those lines, those separating lines, in red. Now, I also drew separating lines in green at negative 2 and 2. We know that to the left of negative 2, capital F has to be concave down. We know between minus 2 and 2, capital F has to be concave up. And finally, to the right of 2, capital F has to be concave down. And again, we know that because we just did it a second ago. So we have this information now about the graph of capital F. But we also need a couple points I'm going to estimate capital F of 2 and capital F of negative 1. So capital F of 2 minus capital F of 0 is going to be the integral from 0 to 2. Now I should have stipulated a moment ago that we're graphing the antiderivative. I may not have shown this. We're graphing the antiderivative that passes through the point 0, 1. Let's estimate capital F of 2. We know that capital F of 2 minus capital F of 0 by the fundamental theorem of calculus would be the integral from 0 to 2 of little f. Now we don't have a formula for little f. All we have really is its graph. And we have some grid lines. So I'm going to estimate capital F of 2. I'm going to estimate this integral using a right-hand Riemann sum consisting of just two rectangles. Of course, that's a very coarse estimate. So let's go over here. So we're trying to estimate this signed area right there. So what I'm going to do is I'm going to draw two rectangles. Using a right-hand Riemann sum, there's the height of one rectangle. And there's the top of the other rectangle. So I'm going to use the combined areas of those two rectangles to estimate my integral. Now it appears to me that the height of this rectangle is about 2.5 and the height of this rectangle is about 2. So if I add together the areas of those two rectangles, their bases are both length 1. I get 2 plus 2.5, that's 4.5. So if I add capital F of 0, which is 1, that says that capital F of 2 is 5.5. Now let's do the same thing. Let's try to estimate capital F of negative 1. By the fundamental theorem of calculus, capital F of negative 1 minus capital F of 0 would be the integral from 0 to negative 1 of little f. And again, we don't have a formula, so we can't compute this, but we can estimate it. Now, the order of integration is unnatural here. We're going from 0 to negative 1. Let's switch it to a natural order where we go from minus 1 to 0 by introducing a negative sign out in front. Now let's estimate this integral from negative 1 to 0 of f of x. So that's actually estimating, that's an estimate trying to estimate that area right there from minus 1 up to 0. That's a negative signed area. It looks to me like it's almost half the area of this rectangle. So that's a 1, that's a 2. So the area, the positive area of this rectangle would be 2. If I half that, I get 1. But the graph is completely below the axis, so the integral would be the negative signed area, which is negative 1. So the integral from minus 1 to 0 would be minus 1 if we approximate it. But then there's a minus sign out in front, so we end up getting a positive 1. Again, the integral from minus 1 to 0, which we approximated using a Riemann sum, is negative. But then we already had this negative sign out in front because we switched the order of integration. So capital F of negative 1 minus capital F of 0 is 1 approximately, which means that capital F of negative 1 would work out to be about 2. And again, this is an approximation using the Riemann sum. Let's put all of this together now with the graph. We know that for sure, we know that the graph of capital F, the antiderivative, so I wrote this up here, but this is really the graph of capital F, the antiderivative. I know for sure that it passes through 0, 1. I have an estimate that it passes through negative 1, 2. And I have an estimate that it passes through 2, 4.5. So this point is for sure, and these 2 points are rough estimates. Now I know from a couple pages ago that within this zone, f has to be increasing, but f also has to be concave up. So that means the graph would look roughly something like that. Now, when we hit 2, the function is still going to be increasing, but now the function is going to be concave down. So it's going to go like that. And then when we hit 3.5, the function is going to become decreasing. So it's going to have to start to go down. Starting at this point, it's going to have to go down like that and concave down. Now within here, we've got this point for sure, we've got an estimate. We know that the function, capital F, has to be decreasing, and we also know that capital F has to be concave up, so it would look something like that. At -2 is where the function switched concavity. It went from being concave down to concave up, but the function was still decreasing. So we're simply going to draw a decreasing concave down function. And to the left of -3.5, we know that the function capital F was increasing, but it was concave down, so it would look something like that. So to summarize the process, what you want to do is you want to look at the graph you're given, little f. You want to break it down into where that graph is positive, negative, increasing, and decreasing, because that will help you determine where your antiderivative is increasing, decreasing, concave up, concave down. Then break your picture up into zones. You'll need a prescribed point. I prescribed that f of 0 is 1. And if you have a graph where you can make some Riemann sum estimates, you can estimate a few points nearby. Here's an example for you to consider in preparation for class. It's a function that looks like this. You'll notice that it has a maximum at about 1.3. It has a minimum at about 2.7. It switches from positive to negative at 2. And we have some grids here. So see if you can graph an estimated antiderivative. Let's suppose that capital F of 0 is 2. Let's see if you can estimate f of 1. And why don't you see if you can estimate capital F of 3 as well? Estimate each of those using Riemann sums. Now remember, over here, some of your rectangles will be below the horizontal axis where the graph is below.